Hey folks, we're starting this chapter 7. You can see by my picture, I got something, yeah. Maybe you didn't expect that. This is a little dub cover of Dark Side of the Moon. So good. So we're getting into this chapter 7 stuff on light, which is very cool stuff. This is one of my favorite subjects, okay? Let's get it going, folks. Oh man, I could listen to this all day. Okay, so we're getting to this chapter 7. So chapter 7 is a massive chapter. This is a really big chapter. I've divided the homework up into 2 parts because of how big this chapter is, okay? So it's all going to be due at the same time. Sorry, I'm doing a timer on my phone so I don't talk too long. So it's all going to be due in 2 weeks from now. But this first part is going to be mostly calculations. So I would highly recommend you making your best effort to get part 1 done in about a week's time. Okay? So let's get it going. So 3 things to characterize a wave. And this could be a wave like in the ocean. This could be a wave of light, or really, as you can see by the title, a wave of energy. Okay, so frequency, wavelength, and amplitude. All right, so frequency is the number of waves that pass a given point in space, or the number of waves per second that pass a given point in space. Okay, so for example, if I look at this one, suppose for all of these, A, B, and C, suppose this length here is 1 second, okay? So what I would see here, if I was counting these number of waves, I would count from peak to peak or trough to trough. So this would be 1 wave, and this would be 2 waves. So that would be 2 waves per second, or I could say that that's 2 inverse seconds, or that's the same as 2 hertz, okay? So the unit of a hertz, 1 Hz, so a hertz equals 1 over a second. And really it's implied that that's the number of waves per second, the number of things per second, okay? So we can see on this one, if I were counting, 1, 2, 3, 4. So this would have a frequency of 4 hertz, okay? So now what about this wavelength thing? So wavelength is the distance between 2 consecutive peaks or troughs in a wave. So that's indicated by both this. You can see lambda, so Greek letter lambda is what we use for wavelength. And by the way, I didn't mention this, but this is technically the Greek letter nu, not a V. It kind of looks like this if you're doing the curly serif-based font. And so this is a Greek letter lambda, okay? So you can see that lambda for A is much bigger for lambda than B. And actually what you can see is, in fact, lambda A is exactly twice as big as lambda B, okay? So there's a relationship between frequency and wavelength that we'll see next. And now finally, amplitude, the height of the peak or the depth of the trough. So you can see the amplitude is indicated by that figure right there. And that tells us the intensity of light. So the brighter a spot of light is, the higher its amplitude. Okay, and we note that we can still have, I can change the amplitude, so I can make light much brighter, for example, or I can make it dimmer without changing the frequency, right? So suppose this is a nice, this is a really large amplitude, it's a really bright spot. I could dim that light by doing the following, right? I just have less amplitude, but it's the same frequency, right? You can see I'm trying to draw the waves in the same frequency, okay? And then now finally, the last thing to describe on this figure, so this whole thing is describing light, which we call electromagnetic radiation. So EM stands for electromagnetic. And when you actually have a beam, so you see how this is a propagation, right? Propagating this way. So we can interpret this as a beam of light going into a direction. Well, as it turns out, there's an electric component and a magnetic component, and they are related to each other by 90 degrees. We're not going to get into this in a whole lot of detail in this class. That's more relevant for physics. But all the same, we call this EM radiation electromagnetic because there's an electric component as well as a magnetic component. Okay, so moving on. So I talked about there's a relationship between wavelength and frequency, and you can see here it is. Okay, so lambda wavelength times frequency always equals c, the speed of light. Okay, so again here, this is wavelength, and this here is frequency. So as I talked about in this slide earlier, this wave has a frequency of 2 hertz, whereas this wave has a frequency of 4 hertz. Okay, and so what we can see here, lambda and nu are inversely proportional to each other. So I'm going to say like that proportional 1 over frequency. Okay, so the smaller the frequency, the bigger the wavelength. The bigger the frequency, the smaller the wavelength, right? So hopefully you can see that on this figure, right? Where this frequency is now twice as big, its wavelength is going to be twice as small, okay? And so now the frequency times a wavelength always has to equal the speed of light. So if we play with these units for a minute, if I have wavelength in meters, okay, and frequency is in 1 over seconds, you can see that gives me meters per second. And when the wavelength is expressed in meters and the frequency is expressed in 1 over seconds, it's always going to equal the speed of light, which is some crazy number, right? Roughly 3 times 10 to the 8 meters per second. To give you an idea of how crazy fast that is, that's 186,000 miles per second. Okay, the circumference of the Earth, so if this is Earth, I'll put an E for Earth, right? And circumference right at the equator. So that's roughly 40,000 miles, roughly, okay? So a light traveling at the speed of light, right, could make it around the planet like over 4 times in a second, in 1 second. So it's crazy fast, okay? We're going to do some calculations with this formula soon.